Hello everybody. Today we're going to be covering new topics, specifically associative arrays, and I'll be doing associative arrays in the context of hash tables. We're going to have likely 2 homework assignments related to hash tables, and so we'll spend some time on that. The hash tables, in my opinion, are where the class tends to peak in terms of complexity and moving parts. I've had some students say that the upcoming homework assignments are the hardest homework assignments of the semester. Not because I tried to make them more difficult, just because you have several objects that are all interacting and students struggle to think in what context are they programming in, what object are they trying to make talk to another object. So it's not so much an algorithm, it's more of a data structure, and I'll walk you through it, but we'll go nice and slow and make sure that we can get caught up on it. I have a homework assignment. I got it out this morning. You'll have a week to get it done. It is an iterator-based assignment. We can talk about it more at the end of class. But for now, I just need to, let's see if there's anything. We don't have a quiz. I'm behind on those quizzes. I need to get a new quiz going soon. Maybe Monday I'll get that quiz out. Beyond that, any questions for me? Doing pretty good? Yes?
When's the first exam?
You know, I like to get through hash tables and then one topic after hash tables. So we're still a bit away. I'm 3 weeks-ish.
Are they going to be similar to the quizzes?
No, as I mentioned before, quizzes are meant to be mean and to force you to learn through repeated trial and error or studying. Yeah, that's not the code. Oh, you're just putting that there to throw people off.
Well, I said it's not the code.
Right, I was just confused why you would say that. It's like, is there a problem? Are you complaining to me? I'll get emails from students. Mr. Peterson, my homework assignment doesn't work. Period. Send that off. All right, I'm sorry to hear that. That's my reply. Anyways, the exams are meant to assess. If I've talked about it frequently in class, expect that it will show up as something that I want you to restate in an exam. All right, so let's get started on associative arrays. These are fun little tricky tools. So we're talking about associative arrays, and in our context they will be hash tables. In other words, here is the main goal of what we're trying to do. Previously, we have been able to associate items in collections. If they had a numerical order, we would often give them a numerical order such as at item 0 we have the data 42. At item 1 we have the data 100. At item 2 we have the data 673, 651, which I am highlighting. But don't read into that highlighting for any useful reason. I'm just highlighting it. All right. Because it is not the code. So and so on. The idea is that we could say, for this integer, I'm going to relate it to this specific number. And that's how you've known arrays your entire programming career. We can make linked lists act in this fashion because the nodes in the list are stored there in a specific order. So as I mentioned on that second homework assignment, we had to get the 5th element, get the 5th node. And so we were able to say, all right, for this int, go get this piece of data. Now this has worked largely for us, but we do have a problem, and we started to see it in some of my demo examples, especially with safe array. What if I set up a capacity of 10 items, and I load the first 4, and then I go ahead and also load 9, but I don't load any of these in between. So they are still garbage up until that point. So you kind of have this weird scenario where, yeah, I've got something sort of I've got plans for node or item 4, but I don't have it yet. So now it's got garbage data. And how did we didn't really have a good answer for it, right? We just kind of, in the back of our head says, yeah, we'll figure that out later. Linked lists, it's not possible to make empty storage space for later. You can cram nodes in between and expand indexes. What we're going to move to is a system that cleans this up, or gives us some more features. So instead of saying an int to data, I'm going to call it some key, which takes me to some data. Further, I want the key to not just be integers. I would like the keys to go much further, and I would like the key to be anything. Most commonly, keys are some string can get me to my data. So instead of saying index 0, I could say, hey, for index Brad, we have some piece of data. Now it's a bit weird that you start putting strings inside of square brackets, because these strings don't really have an order to them. Which one is the first, which one is the last? Yet that doesn't make sense. They really don't have an order. But the idea is to say, you give me the key, I can go out there and get the data for you and retrieve it. Makes sense so far? So for example, let's load up some more data. How much money do you have on you in this classroom right now? Esther, we'll start with you. How much money do you have on you?
Let's go for 0.
Let's go for 0. Is that an honest answer or a safe answer? Safe answer. Now I'm really curious. 20. The name again. Chad. Chad, you are at 20. All right, what else? Let's keep going. I need... Is it Alec? What? You have $1? Malachi, how much do you have on you? No, he's online. That's why he's not here today. 113, holy cow. Manal. 0. Let's hear, is it Steven? Huh?
Steve's my brother.
Oh, I'm sorry.
A whole bunch of change I don't feel like counting. So
Around, give me a number.
$1.72.
$2.
$2. Okay.
You want your $2. All right. We'll stop right there. So the idea is that I want to be able to say, for this specific person, I want to look them up and it gives me this amount of money. Would this have been an easy thing to set up with arrays? Not really, because how do I say Malachi has 113? Do I really have a Malachi integer anywhere? No, at most what I'd have to do is almost create 2 sets of arrays. One that has the name, Malachi, and the corresponding index has the 113. Does that make sense? So you'd have to look across these to find the name, and then come down here to find the value. But then what if you want to add or remove? It gets kind of awkward again to add and remove, right? Now you can start to say, well, maybe I could do this with lists, but now we start running into all sorts of interesting troubles. And I am going to relate this. Yes?
How about a dictionary?
Well, a dictionary is an associative array. How are they structured underneath the hood? That's what we're covering. No, I mean, so let's say I don't just have 6 or 7 of these. I've got 70,000. Now how do I store every person and the money they make? How would you do that? What kind of data structure would you use? Would a linked list of 70,000 items be appropriate? Why? Why was that? Why is that a bad idea?
Because in order to traverse it,
In order to find somebody, you have to hop down 70,000, and hopping down that much that's not good for computers. And computer architecture and linked lists don't get along. They're slow. So what's another structure? Even if you use arrays, yeah, it's faster, but you still have to search all the way down. Someone would say, well, why don't you sort the array? Now what? What's the problem? All right, now you want to start inserting more. Now you have the problem of how do you insert into the middle of the array all over again, correct? So we have the And Malachi says, let's just use the database. Well, what if you were tasked with making a database? This is what the level we're getting at. Somebody out there has to make a database. So I'm going to relate it to, well, let's do more with names. Chad, what's your last name?
Richards.
Esther, what's your last name? Kim? Who else? I'll get one more. We got Malachi. I got yours right up there. Sometimes, if I were to list out more of these, say 70,000 names, sometimes people come up with a strategy. Hey, wait a minute. Instead of having to search down 70,000 names, what if you put everybody in their own array that starts with the first letter of the last name? So Malachi would go into the A group. Esther would go into the K group. Chad, you would go into the R group, and so on. Does that work? Yes or no, and why?
Makes it faster.
Helps.
It helps. Is it a good idea, though? What's a problem with that idea?
What if you just happen to have more people with the last name starting with A, and so that group gets...
It's a distribution problem.
Right.
Are in this country, are all people, is there an even distribution of all 26 letters for the first letter of a last name? No, how bad is it? Is it just a little bit bad and we can deal with it, or is it really bad and we can't deal with it?
I think like the most popular last name.
Distribution of first letter of last name. Let's see if we can find a link on this. This one might do it for me. Yeah, here's your data with lots of ads in between. That's crazy. No. Let's try one more. I don't want to look at a bunch of last names. Here we go. So this is a U.S. Census list. I don't know, this is from 2000. That's pretty recent. Here's their ratios. Which of these letters is the most common? S is at 9.5%. Anything more than that? M is at 9.6. What's a low percentage letter? X, 0.02%.
I. 0.003.
0.03. Does anybody know someone with the last name starting with an I? What's the last name?
Ison.
Starts with an I? Surprisingly, E. 1% starts with an E. Anybody know someone whose last name starts with an X?
Xavier.
No, that's a first name, not last name.
Professor Xavier.
That's his first name. Oh no, it is Charles Xavier. That's fictional, though. All right. So if is this going to work for distribution, or what problems will we have? If you're trying to look up someone with an M, 10% of names roughly go into the M group. So even if I had 70,000 names, I'm still searching down 7,000 for the M's. Whereas if somebody shows up with an I, what's 0.03 of 70,000? I love this. It's a good thing I'm using the trusted calculator. I don't want to use one of those hacking calculators that destroy my computer. Sorry, I'm just being cynical. Oh, 70,000.
I think it's 003.
Yeah. 0.0003. That one?
Yeah.
So 210. Is that going to go a lot faster to search than the 7,000? Yeah, so we have a distribution, we have an unfairness problem. So what do we do to solve this? This was interesting. Somebody in a semester said, well, what if you try to make it something a little bit more random that's not so obvious, like the last letter of their first name? That's pretty good, right? Hopefully that will have, what is the distribution? Distribution of last letter of first name.
Imagine vowels, so it would be more common.
Oh, it's gone through the years. It's like,
All the people called Stan.
Stevens.
Hayden.
Wow.
Isn't that crazy? So is that a good approach, or is that worse?
That's worse.
That's even worse. And this is crazy. It's like I'm always scared of like how much does society mold me, and am I a product of myself, or society turns me into what I am? It's like I looked at this and said, wait, my firstborn son's name, it ends with an N. Did society make me choose this name? I thought it was a good name. What?
That is crazy.
So Malachi jumps in. This is where we start getting into what if we start trying to be more creative. I need to save a copy of this in case I ever lose it. Hold on. 2420 lectures. We'll say last letter of first name.gif. Okay. So Malachi comes back and says, what if we start using more letters of the name? Will that help? And you're starting to get down this road, but you'll start to find out even if you use multiple characters, there's going to be a lot of vowels in it, and those vowels will mess you up. And then you start hitting a situation. I ran into this. I lived in a coal mining town in Kentucky. And boy, you look up someone like my last name, Peterson. There was no Petersons anywhere. You look up something like Sizemore, and in the phone book, there were just pages and pages and pages of Sizemores. Because you get this weird, odd grouping. And so now you start having to account for that. And so it starts to become a problem, right? Yes?
So, what if you turn all the letters of the names and numbers?
No, it doesn't work that way, though. Because I've tried it, and you start having this grouping problem where vowels it does mess you up. There's a better approach. You can try to turn it into the vowels into numbers and add them up and divide or something, and you start to get there, but it's not good enough yet. Interestingly, there is supermarkets have kind of solved the problem, but not how you would expect. For example, when you go to a supermarket, are pretty much, let's say it's a boring supermarket, it's just a bunch of aisles, it's a boxed store, they don't have funny side aisles. Are all the aisles the same length?
Until you get to the diary section.
Well, I mean, if you get like the medicine section, but I mean, for a lot of stores, you'll have like, hey, there's 20 aisles. Those 20 aisles are the same length. How'd they do that?
If they need more space.
And it's not like they just wrap candy around. They actually say, no, candy's limited to this aisle. This product is limited to this aisle. This product is limited to this aisle. So they've got a system where they can start to group by category, and by that category, they can then give you an ID number of sorts. And that ID number then says, go down this aisle and find your product. I mean, wouldn't it be weird if you went to a supermarket and you were confused and you say, hey, I need to know where the milk is. And the store owner says, okay, that's down aisle 1. That's the array-based approach. All right, we'll do eggs. Where are eggs? They're also down aisle 1. Cereal. What do you also go to the store for? What's some good purchases? Dog food. What else?
Bread.
1, bread. And you keep asking all these questions. Candy, it's down aisle 1. Toys, they're down aisle 1.
Wasabi peas.
And then you stop asking, wasabi peas. You start making up stuff that doesn't exist.
That exists.
Good jazz music. It's things that don't exist. He's like, I can never look at you. He doesn't like that joke. He's like, well, they say it's down aisle 1. Because everything's down aisle 1. It's this new store. They bought a plot of land next to the interstate. It's 100 feet wide and 2 miles long. It's called the exercise store. You get your exercise while you... Wouldn't that kind of be fun? You do it once just to take a picture, a selfie, put it on Facebook. You just go for 2 miles, just walking down one aisle, see what all the products are, grabbing stuff, walk all the way back, check out. Is that an efficient way, though, to organize things? No. So what we need is we are after fast lookup, and we'd prefer to do it with excellent distribution. In other words, if I go back to this name system, I want to be able to, I hope that whatever system I have, I can look up any person or any key in roughly the same amount of time. Does that sound like a fair requirement? Yes. Now you start going down this approach where we said, well, what if you take letters and you turn them into numbers and adding them up? And it starts to work to a degree, but it has problems because you're starting to craft very unusual solutions just for that key. Then what if somebody comes along and says, all right, we can no longer use first and last names because of FERPA violations. Now you have to use W numbers. Will that work? Will your same approach work? May not, because you may find out the distribution of W numbers isn't random. And so you start finding out that when you add stuff up and do math, that they all show up in the same locations. Does that make sense? So we need to come up with a system to make a generalized algorithm for the distribution. Where do you go look for them? And it also means in order to have a good distribution, it helps to have what I call many buckets. If I did first letter of last name, I have 26 buckets. If I want to say, well, let's do the first two letters of the last name, now it's 26 times 26. 676 buckets. Maybe that helps, maybe it doesn't, but I have more buckets. More buckets help spreads out the data. Does that help? We will use a tool called hashing as the key or the main feature to make this work. They are the main feature of what's called a hash table. Some of you have heard hashing before. People in the class have mentioned it. Online students are mentioning it. What is a hash algorithm? What does it do? Do you know? It doesn't deal with buckets yet. Let's look up SHA-256. It's a very common hash calculator. We'll try this one. All right. So I'll put my name in here. Take the name, I'll calculate the hash, and here it is. Let's stick that in Notepad here so you can see it. For Brad, it came out to this. Esther, let's put your name in here. I put Esther in. Here's what it came out as. Who else do I want to choose? Who do we have? Chad. We'll use Chad and Malachi. Come back here. Chad. We'll hash you. Malachi. We'll hash you. What are you noticing about this?
That you spelled.
Whoops, I did say hash, sorry. I can't type and think at the same time. Yeah, I don't know if you've ever tried to chat with somebody or write an email while you're talking on the phone on something entirely unrelated. Like your brain just completely unwires and hooks together and it's not possible.
Well, they're all the same length.
They are all the same length, that's very nice. What else? It's using hexadecimal. And hexadecimal is just shorthand for binary. Let me change one letter. Esther, what would be an unfortunate letter to change in your name? Anybody, what would be a letter we could change?
You could add a P.
No, I'm not going to add.
If you take away H.
Esfer.
Oh, that's fine.
How's that? She approves. All right, here's Esfer. I changed a single letter. What do you notice about the two hashes? Completely different. SHA-256 is, how do I put this? Well, let's do a little distraction or side talk about hash algorithms. They're a fundamental tool of computer science. They have lots of uses for many different applications, and we're going to use these specifically for our needs in a hash table. But the main idea of a hash algorithm is that it is a one-way, a good hash algorithm. You can think of it as this. You take your data and you put it into some kind of a, let's see if do you remember the old Batman TV shows? They always seem to have the conveyor belt torture device. Let's see if I can draw it. They strap the heroes down and no, they're going to have to. I think they actually got out of it by singing on one of them. It's a good episode. I like those old Batmans. So here is the hash machine. The idea is that you put your data into this hash machine and out comes some data. It's 28B8502387006FD. You get the idea, correct? So if you stick in the data again, will you get the same hash coming out? Yes, it is not random. There is absolutely no randomness to hash algorithms. It is repeatable. You take the exact same data, you put it in, you get the exact same data back out. You can often think of it like, oh, I don't know, I'm a terrible artist. Let's see if I can do this. This will be a cow. Utter terrible. We'll put some spots on here. It'll make it a cow. Give it some Texas Longhorns. No, the horns. You see that? Yeah, we got to give it a bell. Moo. There we go. That can't be a dog now. All right. Horns and udder. This is a stereotypical cow. What happens, the idea of it is that you want to think that it mucks up your data so much that when you get done, it turns into, we'll put some grill lines on this, the hamburger. The whole point of a cow is to make hamburger. Would you be able to take all the hamburger that was made and undo it and get the cow back out?
According to alchemy, possibly.
So the idea here is that you want to make it so that whatever data you put in, you can't just look at the data and figure out and somehow do a reverse algorithm. It doesn't go the other way. You can't just take the data, undo it, and get your original data back. Does that make sense so far? So for a lot of reasons, hashing is commonly used to store passwords. Do you actually store the password in a database? It's usually a bad idea. I'm no fan of it. So what would be an alternative if you can't store a password? You store the hash. How does that help? Now let's say your server gets rooted, someone has access to your database, and they go look at the password table. Now what? Can they see your passwords right off the bat? No, what do they see? A bunch of hashes. How does that help them? Not really. It can. It gets us somewhere. But the idea is it's a level of security, correct? And so the idea is you supply your password, it immediately hashes, and it compares the two hashes. If the hashes compare, then that must mean you knew your password and it lets you on in. Now that said, if you made your password, this is commonly done, is instead of trying to, when databases are stolen, there are some list of very common passwords. Or in other words, what people will do is they'll just create this giant database of existing hashes. So they'll go through and take every single English word in various combinations of 6 characters and throw it all in and make these giant terabyte-sized databases of hashes. So that if anytime they ever get one of these databases, they actually look in the database for the hash and they'll do a reverse lookup on it. In fact, let me see if I can find one. Reverse SHA-256 lookup. So this one hopefully is reversible. I'm going to try to decode this guy. And it's not that hard. Yes, what did it decode to? Now, did it actually somehow do math to undo it? No, what did it do? It looked in a database. So when they say decode, I don't like the word decode. It didn't actually decode. It just straight up said, oh, I've seen this before. That's why they want you to have interesting combinations of numbers and letters so that it's harder for someone to do a giant brute force attack and find your password.
They're called rainbow tables, yeah.
Rainbow tables are slightly different. Rainbow tables use some really clever math to chain results on top of each other, and it makes it more efficient. It makes it not perfect, but it also means it's more efficient. It's weird. We're not going to get into rainbow tables. I'm talking about just straight up brute forcing.
So can you make up like a crazy password that I won't be able to find?
Yeah, so I'm going to try one right now.
We'll see if you looked at Malachi.
Hold on. Yeah, let's see if I can go back here. I'll be impressed. Well, they might actually, I'm going to do it somewhere else because often if you put it in, they immediately save it in their database. So let's go back to our calculator here. Sesquipedalophobia. That is the fear of long words. Nobody thinks that's funny? Come on, guys. That's awesome. All right, I'll try to decode it. Let's see if it knows about it. No match found. But if I tried it over here, sesquipedalophobia. Hash it. They just want me to look at their ads. It's not that hard. Hashes are supposed to be fast. Oh, they're doing a bunch of hashes. That's what they're going at. Just so you know, MD5 used to be common. It's broken. SHA-1 used to be common. It's broken. SHA-256 is really common now. It has no hint of being broken anytime soon. There's some other weird ones out there. Most of the world uses SHA-256. Let's see if we can decode it. Whoops. All right, so let's go back here. Try to see if it remembered it or not. Come on. Yeah, see, they added it to their database just now.
So don't use that for your, to see what your password.
Right. Now you will find that another common need for hash algorithms is that you want these things to be fast. Slow hashes tend to not have, well, I guess they do have some practical application now in terms of bitcoins, but I'm not going to deal with those. Usually you want something fast. A good example of a reason why you want something fast is, let's say you're just deeply suspicious and you're downloading a file off the internet. It's a big 10 gigabyte file. And you need to verify that all the bits of those 10 gigabytes came to you unaltered. How do you verify that it all came to you unaltered? That no one somehow snuck in midstream and threw some little bits into your download? What do you do? How do you verify it?
If it's a good developer, they'll provide the hash.
They'll provide the hash of the 10 gigabyte file. Or what you can do is you could let you call a buddy and on the phone just say, hey buddy, I just downloaded your file. Can you hash it? SHA-256 hash your 10 gigabyte file. Okay, bam, it's done. Here's your hash. Person on the other end does it on their own file, hashes it. If the hashes match, what does that tell you? Should be good. Now, Nathan said, what if you use something like MD5 hash? No. People have done the following. Let's see if I can show you. Does it have it here? think is it this one? Here we go. Instead of downloading it, I'll just show it to you. The idea here is, this is Google pulled it off. Oh, where did it go? I needed that image that I just saw. View image. This will work. If you try to do SHA-1 there's two PDFs that you can download. If you ran SHA-1 against this PDF and SHA-1 against that PDF, guess what you get for your results? The exact same hash. But what if you use SHA-256 against both PDFs? What do you get? Different hashes. In other words, what does that tell us about SHA-1? It's broken. For the purposes of this need here. MD5 was broken over a decade ago. So we don't use SHA-1 anymore. What was that? You can hash any file, yes. That's how these for these kinds of hash algorithms we talk about, they're designed to work on any size file. You can even hash a single letter.
That's the cool thing, it's like this. So that you could hash the entire hard drive, and then if anything ever changes,
Yeah, that's a common way for backup systems to verify. Instead of trying to back up by file name or back up by date, what they do is they just look at they'll look at files in just block size. Okay, let's take a 1 megabyte block of your file. Hash that one block. Have I backed up this block before? That way, if you move your files around, you change the file name, you duplicate them, it knows how to just say, no, I just need to back up one instance of this block. So it's got a lot of practical purpose. For us, the only thing we need hash tables for is to give us excellent distribution in the many buckets. Of course, I also want the fast feature here. So how can I use these kinds of hash algorithms to go into many buckets? What can I do? How can I make sure that Brad goes into one bucket, Esther goes into another, Chad goes into another, Malachi goes into another, and have even distribution? What could I do with this data? Any idea? We'll go back to our original example. What if I pick the first letter, or the first hexadecimal letter? Do you remember how that didn't work for last names? Well, is it going to work here? I've made you too paranoid. Yes, and I turn around and say, no. No, it should work, because the idea is that these things they have excellent distribution throughout. You just can't find patterns. So at this point, if you were to pick off the first character, you now have 16 possible buckets, because it's hexadecimal. What if I need more than 16 buckets? What if I want 256 buckets? Maybe grab the first two, or the last two, or whatever group you decide on, but just grab 2 of them, correct? What if you want more buckets? 4,096 buckets. Now what? Grab the first 3. What if you want a jerk amount of buckets? 91. A prime number.
You would go to the higher one and just not use.
No, there's a better way to do it. There's actually a really easy way around this problem. Somebody wants a prime number amount of buckets, because they can.
Use a modulus.
You use mod. Treat this guy as a number. Mod it by that prime number. Mod it by 91. What does modding do? It gives you the remainder. So if I mod by 91, what are my possible results? 0 through 90.
Okay.
And will it be well distributed? Yes. Does that help us out?
Yes.
All right, now we have all the tools we need. So here's going to be the process. We start with a key. I'll say identify or obtain a key. Key could be a name, it could be a W number, it could be whatever you want it to be, because it could be a 10 gigabyte file. I just need something I can throw through the hash algorithm. Make sense? Number 2, apply the hash function or hash algorithm to the key. Pay attention. I'm gonna endlessly talk about these steps because it never seems to stick in students' minds. But just, you really want to, if you get this concept down, it makes the rest of these next 2 weeks a lot easier. Apply the hash function to the key. A sub-step, I'll call it step 2b. Apply a mod to the result. You would mod by the amount of buckets. So if you have 91 buckets, you would mod by 91. Make sense? Now what? You take that result,
Then you apply that to the key.
the result from 2 tells you which bucket to use. Make sense? If you mod by 91 and you get the value 73, what does that tell you?
They go into bucket 7.
The data you're after will be involved or related to bucket 73. Let's say we're just trying to do an insert of data. Then what? So you go to that bucket, I'll say as part of 3, go to that bucket. Since we're doing insert, what do you insert into the data? Let's say I hash Malachi, and I mod Malachi, or I take the hash result, I mod it by 91, and it tells me 33. So I go to 33. What do I store in bucket 33? Do I just store how rich Malachi is and store $113?
You should probably store his name too.
I should store his name as well. So I should still store the key associated with the value. You can't just store the value because now you don't know what the value. Could there be more things going to bucket 33? There could be lots of things showing up in bucket 33. So I need to know, okay, in bucket 33, which piece of data do I have? Insert both the key and the value. All right? If it were a lookup, instead of inserting the data, you want to look up the data. Would these first 3 steps still be the same? Yes. Then what would you do for 4 on a lookup? You only have to go down that bucket looking for a matching key. What if you find the matching key? You find it, return the data. Does that make sense? Does that, let's compare what we needed for our goals. Does this give us excellent distribution? Yes. Is it a generalized algorithm for the distribution? Can I throw any kind of keys, any size of keys, and still get generalized distribution? Yes. Is it fast? Does it allow us to have an arbitrary amount of buckets? Yes. How fast can the lookup be? And this is a good question. How fast is this? All right, let's do students at Weber State. Take a rough guess. How many students do you think have ever been at Weber State?
Ever been this semester?
Ever?
Well, at least 140,000.
I'd say what, 200,000?
200,000.
Yours is very specific. Is there a reason why you had that?
W number?
Did you look at like some factoid or something that said that?
No, it's based off of W number.
Well, W numbers, they used to be sequential, but they aren't anymore. I'm going to say 200,000. All right, I want to have a hash table that stores 200,000 students. How many buckets should I have? Well, hold on. What would be a good key for 200,000 students? There's a really natural key to use. The W number. Makes things very nice. How many buckets do you think is a good amount to store 200,000 students? Should I have 10 buckets? 20? Well, if I did 10 buckets, and since we now have good distribution, roughly how many students would there be per bucket?
20,000.
Per bucket, 20,000. Is that what we're after? And a lookup. You jump to a bucket and now you have to search down 20,000 to verify, to find one of them.
So it takes a while.
Still takes a while. So what would be better? Grace is getting bold. She says 20 buckets. Did that help, Grace? You have improved performance. If you're a salesman, you have improved performance 100%. Look at this. It's 2x speed up. This is amazing. Everything's twice as fast. Is that good enough yet? Why?
I don't want to do that much.
There's still 10,000 people per bucket. Malachi's going crazy. He says, why not do 100 buckets? All right, he's getting bold. Jeff's going to one-up him like in the Price is Right version. No, sorry, Malachi, we don't care about you anymore. Jeff has one-upped you. We now have 101 buckets. How many are there per bucket?
Roughly
1980 per... Is that still good enough yet? Nathan is just going, hey, well, you know what? Let's just do 200,000 buckets.
Yeah. One person per bucket.
How about 449 buckets?
How much?
449 buckets.
449?
Yes.
How about we use 673,651 buckets?
Well, that's a lot of dead space.
That's a very specific number, which I have mentioned for no reason at all, other than to confuse you. All right, 200,000 buckets.
Now you're spending too
What if
much
we said we
time.
wanted?
Hold on. Is this a bad idea?
Yes.
Why?
because now you have 200,000 buckets you have to search through.
No, hold on. Have I taught you nothing in this class? You have 200,000 buckets you have to search through. No, how do hash tables work?
Oh yeah, that's right. You just take.
Okay, you take the key. What do you do to it? You hash it. Then what? Mod by the amount of buckets. Can I mod by 200,000? Yeah. Now what does it tell me? A very specific bucket number to search down. How many students on average are there per bucket? 1 student per bucket. Will there be some buckets that have 2 or 3 students? Yeah, will there be some buckets that are empty? Yeah, but now how fast is our lookup? That's about as fast as you're going to get. I mean, think about it. We had 200,000 students. What did we do? We hashed the key. Is that a fairly fast process? Yes. SHA-256 over a small W number. Then what? We modded the result. Is that a fast thing to do? Yes. Then we went to a bucket. Is that a fast thing to do? Yes. We searched a bucket likely only containing 1, maybe 2 students and found it. Is that a fast process? Yes. Can you do better than this? I mean, at this point, it was just bam, hash, bam, mod, bam, go to the bucket, bam, search your data. It's almost certainly that one right there. And you've got your data. You have just split the process of looking up 200,000 students into just a few steps.
Why don't they do that?
They do it that way. That's how databases work.
Because I don't know. Up until this point, I've always been told don't split it into that many buckets. Like,
Why not? Well, your limit is the amount of RAM and space. So now with hash tables, we're now starting to consider practicality. You know, someone says 200,000 students, but no one went crazy and said, why don't you just do 1 billion buckets? Why not? What limits us with 1 billion buckets? Hard drive space, RAM, whatever we're working. At that point, you now have to start taking into account, all right, yeah, you don't want to install a 2 terabyte hard drive if you don't need to, just for that purpose. So you do want to start being practical in your decisions. How many of you have done the database class, 2550? A lot of you? Will you have to write your own SQL statements? Do any of you remember having to index a column of a table? Nobody did this? Did they not teach this in 2550?
I might have just don't remember.
Do you remember what happens? Why would you index a column of your database? It goes, if you got a whole bunch of records in a database table and it's slow to look up, the common thing is, well, let's index on this ID value. And then the database churns around, it does stuff, and it comes back, says, okay, and then you do your SQL statement again, and it's a lot faster. What just happened behind the scenes? The database set up some kind of a structure so that instead of looking at your data like a flat array, it now has a structure under the hood so you can find your data much, much faster. I know when I use MySQL, I want to index the table, and it gave me 3 options. And one of the options was, do you want to index with hash tables? I mean, these are powerful things. We're hitting enterprise level data structures that get the job done. So Grace, you had a comment earlier and I shut you down. What were you going to say in our bucket guesses?
Oh, what if we said we wanted like 5 items, like in each bucket? Could we like go back?
But yeah, so what if you want to set the rule? Okay, I want 5 items per bucket. It's a reasonable amount, right? You just have to search on average 2.5 to find it. So now you simply, that tells you, okay, I want 5 per bucket, so I want 40,000 buckets. How it works. Now you mod still, you mod by 40,000, and everything else works. Is that good so far? All right, we're almost there. Now what we need is just download more RAM. I wonder if there's a product that lets me do that.
You ever seen this?
This is going to be good. I'd like 8 gigs, please. Yeah, I like that. Okay, let's download it. Yeah, this easy. Interwebs. Retrieving all the RAM. Hope I don't steal somebody else's RAM. They may need it. This has got to be good. Come on. Click for more info. They're setting themselves up for a great joke, and yes, that was a good payoff. That makes me happy. Welcome back, Malachi. All right, so now we're getting there. Now what we need to do is figure out a data structure to hold 200,000 buckets. How do I actually store this data now? I know I have this mythical amount of buckets. How do I make 200,000 buckets? What do I do? So we got the concept in place, but now we just need the data structure. How do I store 200,000 buckets? Give me ideas. This is going to be another challenging problem. Yes?
I have 2 ideas.
What?
A 200,000 spot array.
Okay, so you want to have an array,
2D array.
a 2D array.
Or
Hold on, got one 2D array that is 200,000 by 200,000.
nah, the Y value.
The Y value can just be whatever we expect the max one to be. Let's say that one bucket will get really unlucky out of 200,000 students. Maybe I need to have 10. Because you might have one bucket that really fills up, just by distribution, unlucky distribution. Or
A 200,000 array of linked lists.
a giant array of linked lists.
Yeah.
How many linked lists then do you want?
Have the 200,000 linked lists.
200,000 linked lists. We're going to take the attitude of Joe and say, no, that's too big of a number. Computers can't do big numbers. 200,000 linked lists. Are you crazy? Computers can't do that. Other ideas?
Well, 449 lists.
All right, let's go down the 2D array approach. Would this work? A 2D array, 200,000 long, 10 deep. Why did I make it 10 deep? For that one special bucket that might have 10 items in it. Correct? What's an upside? Tell me something good about this approach. We're hitting a point where there's no right answers. It now all starts to depend, and you have to tell me why it depends. What's something good about this? Arrays are fast. That's always a good... The arrays are fast. What's...
You can mod key because it's already in a number, and that's where the index is at. So.
No, that's going to be the same anywhere.
Oh, okay.
Any other goods? What? Easy to search? Yeah, you hash Malachi. Hey, Malachi's in bucket 113,477. So what do? Go to that index and then start going down those 10 items in that index to see if I can find a matching key, a matching W number. What's a bad thing about it?
What if there's 11 in the bucket?
What there's 11 in that bucket? That'll happen. What this is a mission critical application.
Because it won't be like.
I mean, you can get unlucky. You might just have somebody, somebody realizes, hey, I mean, it's called the adversary. Think of the adversary as being the jerk. In religion, you have God, Satan. In computer science, you have the computer engineer and you have the jerk. That's the religion here. The adversary is the jerk, recognizes that your data structure uses SHA-256 and uses a 2D array. If I were the adversary, you know what I would do? I just do a whole bunch of hashes and I look for just a whole bunch of pieces of data that I know hash exactly to that bucket. And then I just keep loading it on up. Why? Because I want to fill up that one bucket over and over and over again with more and more and more data. What does that do? Fills up the 2D array, and let's say, well, okay, we'll just start resizing the 2D array to keep making it fit. Well, you got the resizing problem, and I keep loading on data. What if I find, say, 10,000 items that work? Or I find 10,000 items that work. Now what?
You're going to,
How big is that array at this point? 200,000 times 10,000 is what? You can count by zeros. 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Is that a big number? I now have a 2 gigabyte array. Did I need that? I need a minimum of 2 gigabytes, but that's if it's all single byte data structures. If it's like a double, multiply that by 8. If it's an object that each needs 1,000, multiply it by 1,000. At this point, it's becoming impractical. Like you can't even fit it on most hard drives. So 2D arrays have problems. Bad, lots of wasted space. Bad for mission critical. How do I say it? One bad clump ruins it. Do you understand what I mean by a clump? You somehow, everything went into the same bucket. Other ideas that you have then on this? A vector is just an array. Do you want to use just one array, or do you want a 1D array or a 2D array? No, you guys get to design it. If it works, it works. We talk about what's good, what's bad. A 3D or 4D array? Why would you go to 3 or 4 dimensions? What will that do for you? Now in computers, you can think of a filing cabinet within a filing cabinet within a filing cabinet within a filing cabinet. In physics, 4D is time. We're not talking about some temporal data structure that can go back in time and... That would be a really fun data structures class. Side note, it's at 6:30. I can take a small little break. One of the best... That's my already up here. Is this it? Chronoton, yeah. If you ever want a fun game to play when you're bored, I won't play it right now. It's a game where you actually there's a version of yourself and you have to go into this room and do specific tasks, and then you go back in time and have to interact with your past self and cooperate with your past self to help cooperate together to solve challenges. And you have to have 3 or 4 versions of yourself all trying to do things and getting the timing just right. And you set up these weird paradoxes where you murder your past self, which means that you don't exist, and it's pretty fun. I like the idea. Okay, so other ideas? None? It turns out 200,000 linked lists is a very valid approach. Another approach is a 1D array. Not a 2D array, but a 1D array. And specifically, I'm actually going to use, don't get confused by this, 3 1D arrays. This isn't a 3D array, it's 3 1D arrays. Let's talk about this one first, and then we can talk about this one second. A quadri-linked list. That would just be something that does your piece of your data. You have links going up, links going to the right, links going down. Now, as far as a data structure goes, these aren't common. As far as network topologies go, these are actually common. In fact, what they will do is they'll go one step further, and they will have hyperloops into it. So they'll have rings built into it as well, so you can have more dimensions. We're not doing that. Doesn't help us in this problem. All right, so let's go to the 1D array, and let's go back a bit simpler here. Let's make an array to hold keys. Let's make an array to hold the value or the data. And I am going to make 8 of these. So 1, 2, 3, 4, 5, 6, 7. All right, let's go down the classroom. I am going to say whatever we do to our keys will be our first name. The hash algorithm, whatever it is, we will mod by 8. I will have indexes 0 through 7 to work with because I am modding by 8. Grace, you missed it, so I'm going to start with you. How much money do you have on you at this very moment?
I think I may have like 26 cents.
26 cents. Okay, we'll round down to 0.
Sounds about right.
All right, so Grace, give me a number between 0 through 7 that you hash to. I'll let you decide your own hash value. What do you hash to? What?
6.
6. So the idea of this is that I go to 6 and I'm going to put the key. In this situation, the key is the name. And for the value, I'll have a little object in here. And this object will actually have the money value inside of it. I could put more stuff in here, like Grace's age, Grace's Tinder profile. But we're going to put, wouldn't that be great on Tinder? They'd say, all right, here's the name, here's the photo, here's the amount of money. That'd sure change up Tinder, wouldn't it?
Be interesting, that's for sure.
All right, let's keep going. Esther, what do you hash to?
3.
You hash to 3. And Esther has a very safe $0. Was that right? You have $0. Was that what we had you down to? Gotta verify this. Where are we at? Yeah. Also with 0, that's our data. All right, Chad, what was it? You had 20? What do you hash to, Chad? 5. Oh, 20. Is that right? All right. Alec, what do you hash to, Alec? Are you specifically, did you pick 4 because you like the number, or did you pick 4 because it's empty? You like the number. All right, that'll work. How much money did you have on you? What do we have? Let's go look it up. People forget. $1. All right, Joe. You had $2. Joe, what do you hash to?
0.
Why do you say 0?
Because it's the first, so it's the best.
I had a lot of jokes and I'm not going to say any of them. Joe, you had 0, correct?
2.
Oh, 2, that's right.
0, that's fine.
Manal, give me a number you hash to. Please pick a number that's been used now. That's kind of the whole point of this exercise. You don't pick numbers that are free. You don't go to the hash table and say, what's open? That's what I hash to. If I'm going to roll dice at this point.
I've got a,
You don't give a
I got a
choose.
D20 ring.
Do you really?
Yeah.
No, is that?
It's an actual D20.
That's the cool. All right, roll it for me.
All right.
If it doesn't go between 0 and 7, we'll just keep re-rolling.
Oh, sorry.
That's like you can make your whole life decisions on that.
Yeah.
It's like I'm gonna eat which restaurant. I'm gonna try to kiss this girl. 20, that's a crit. I'm gonna do it.
Good thing she's not white. Yeah.
All right, what did it hash to?
3.
3. All right, hold on. All right, that's a good one. Manal,
Brown hash is supposed to not be random.
no, it's not random, but we're assigning this value, and I throw Manal through a hash generator. No, 3. Yes, we know you live a very crazy life, Vegas, everything. Every time you get a paycheck, the first thing you do is go across the border. Manal's a very wild person.
It was the team logo. It's the market.
All right. So Manal, if I try to put you at 3, what's the problem? I have somebody there. We have a problem. How do we solve this problem?
Hash her again.
No, so it would be the exact same thing.
No, we're not going to hash again.
Put her through a different hash algorithm.
There is, now that is an approach we can take. We're not going to go down that road right now. We're going to keep this simple.
Compare them and then move one down.
So the problem is Esther's there, correct? And so the 2D approach says, well, why don't we just make more rows in our data so that, hey, I need more stuff for Manal to show up Manal's data, correct? What did we learn, though, about this 2D array approach? It can take up a lot of space, and it's easily abusable, correct? So what do we do instead? Another answer is to say, you know what, how long has it been since we've seen Esther? Do we really need Esther in the database? Can we just delete Esther? I mean,
She doesn't have any money on her.
actually, this was a Supreme Court decision from yesterday. Hey, we haven't heard from you in 2 years.
All of the voting.
Yeah, we haven't heard from you in 2 years. Can we take you off the rolls? If you don't respond and we don't see you in 4 years, we're going to take you off the voter rolls. 5 Supreme Court justices says that's okay. 4 said you can't do that. And we're going to say, yes, sir, we haven't heard from you for 6 years. We're just going to get rid of you. And that way we have room for Manal. Is that a good approach?
No, because if you lose Esther.
No, it turns out the approach we're going to take is that we will look and keep going until we find an open bucket. Is that one open? No. Is this one open? Is this one open? Is this one open? Yes. So now I can put Manal's data. Everybody here has $0 on them. And now I fit that in. Now we have some problems that just introduced. For example, now I want to go look up Manal. What do? I hash Manal. What does that hash to? 3. What do?
Then you have to step.
I have to go start stepping down the array until I find it. Yes.
So did it start from the third index?
It started from index 3 because Manal hashed to 3. All right, let's keep going. Joe, we've got you in the back. I'm sorry, it's Alexis. Alexis, how much money do you have on you?
I don't know.
What? 0 also. What do you hash to, Alexis? Give me a number. No, run our algorithm.
Give me a number.
6.
6. Alexis hashes to 6. How much was that ring?
$20.
Did they actually spin the ring and that was the value? Oh, yours is
I
20.
know, huh?
All right. So Alexis hashes to 6. Where will Alexis end up in my array? Do we say, oh, we're out of room, we can't do it? No, you wrap around. So where will Alexis end up? At 1. Your data was also $0. All right. So is this starting to have problems?
What do you do when it's full?
What do you do when it's full? You would rehash, which is a common thing. You basically create a new hash table that's maybe twice as big, and you go through all the individual items one by one. You rehash Joe not for 7 buckets, but now for 16 buckets. And then put Joe in the new hash table. And Alexis, let's say it doesn't hash to 6 anymore, now hashes to 13. Alexis would now go to bucket 13. So if it fills up, you would rehash. Does that make sense? You don't believe it? Do you want to see me draw it out? You just weren't like, yeah, that makes sense, I get it. Or do you just not like it?
That's good.
No, I was doing that darn Game Maker game today. I just hit a point where I hate this. I just don't like this. If this was what computer science would, I'd be going to another industry. I think I get that feeling. So let's talk about some good and bad about this right now. So what's something good and bad about this approach?
It's pretty quick to put in data.
It is still fast, and what's the reason it's fast? Because it's arrays. Remind me next time. I'm going to talk exactly why arrays are fast. I haven't covered that yet. All right, what else? What's something good or bad? So you have to rehash if it fills up, correct? There's another problem. It's called clumping. Where did Manal end up? 7. Where did Alexis end up? 1. So in other words, Manal actually made Alexis end up at 1, even though Alexis had nothing to do with Manal's number. Does that make sense? Manal was wanting to go here, but ended up here. Alexis wanted to go here, but ended up here. So the two had nothing to do with each other, but they clumped together and made one really big, ugly clump. Does that make sense?
Yeah.
And what's the problem with clumps? They affect performance. Your lookup times are worse. Now instead of just trying to look up one piece of data, you have to start hopping down a lot more to find it.
So could you make another array that holds the index number of where they ended up?
No, you can. We might talk about tricks next time. There's always. We're hitting a point where these data structures, there's no right answer, and you can start doing tricks and tweaks and things to improve on it. But for now, we're keeping it basic. One good thing about this is it works well for systems that don't have dynamic allocation. Sometimes you're in an environment where you just can't use a new keyword. Hey, I needed to have a fixed size array. All right, I can work with that. But you do have to rehash. The performance dips. Performance dips as it fills. Does that make sense? You get more clumping as it fills. It has problems as it fills. Also, wasted space as it starts. Hey, I know I'm going to store 200,000 students eventually, so let's make this giant array, maybe 400,000 spots. Now you have a whole bunch of empty spots that you're not using.
But it's still space out.
It's allocated there. There's another one we haven't dealt with yet. We ignored Esther for so long that she actually dies. It's a very sad death. But no one came to her funeral because we ignored her. This is a terrible class. Wait till we start talking about trees and we have parents and children and parents murdering their children. We have a lot more fun there. All right, so Alexis is gone. Do I just get rid of Alexis out of the, or no, Esther is gone. Do I just get rid of Esther out of the database? If I got rid of Esther, what would happen? Hey, Manal, let's look you up. Manal, what did you hash to? No, what did you hash to? 3. So what do? I come to 3. Are you there? No. What do I conclude? She must not be in the database, in the hash table. How do we fix this problem? What was that? How do you know to rehash Manal when Esther went away?
Every time there's a death, you rehash.
Every time you delete, you rehash the entire database? That doesn't sound efficient. What's another solution to this?
If it's empty, look forward.
So if you find an empty spot, just keep looking.
Just look until you reach.
Wait, isn't that called an array?
Yeah.
That now you're not doing anything hash table anymore. Hey,
What if
if-
there's a mistake and she's never in the database?
right, what if you're looking up somebody, I look up me. Hey, where's Brad in here? If I follow Joe's approach, I have to look down the entire thing to verify that I'm not in any of them. Isn't that kind of defeating the purpose of a hash table?
Yeah.
So what do we do to solve this problem of Esther dying?
Resurrection.
No, well, one approach is you just don't let people delete. Like, no, we got to get rid of. We need to make sure that this isn't in the database. I need to know that Esther's not here. What do I do? This is an actual real a common computer science answer to deleting is you don't actually delete. You just mark as deleted. In databases, don't delete, just mark rows as deleted. In file systems on computers, when you delete a file, it doesn't really delete the file, it just marks the file as deleted, but the data's on the hard. When you deallocate, does it go and zero all the bits in memory? No, it just marks it for reuse. So how do I mark that it's been deleted, but not actually delete it? A Boolean where? Where do I cram the Boolean?
You said the data was an object, and so you could have a Boolean in there.
I could have the data in the object. I also said that I would use 3 1D arrays, but I only drew 2 of them. Here's the third array. It's a status array. And this can act. And you said use Boolean. So if they're alive, what's the Boolean value? True. All right, if nothing has been used, there's nothing in here, what's the Boolean value? False. If somebody is dead, what's their Boolean value?
Yeah.
But now we got a problem. Hey, I want to start. Something hashes to 2. How do I know that this one was something there, and this one in a 3 there was never anything here in 2, but there was something here in 3. Do you see the problem? Like, I know that if I ever hit a 3, I want to keep looking to find Manal, correct? But if I hit a 2, do I need to keep looking? No, 2 is truly empty. Is Boolean's going to cut it for us? No, so what do I do? Is it?
So there's only 3 possibilities.
There's 3 possibilities.
Can you do just like a short one?
We'll just do an integer.
Okay.
If it's empty, do it as 0. If it's used, do it as 1s. If it was delete, do a -1. Why does that help us? Hey, Manal, I want to look you up. What do you hash to? You hash to a 3. I come to the 3, and what's the first thing that I check?
The status.
Check the status. What does that -1 tell me? There was something there, so do I keep looking? Yes. Otherwise, if say you were, let's say I did somebody else, Brad, am I in the database? I hash to a 2. All right, so I start at the 2, and what do I see? What does that tell me right off the bat? I am not anywhere in the database. I don't have to keep looking. Does that make sense? If I were to hash to a 2 and I try to look up and see if I'm in the database, if I see a status of 0, then I can guarantee I am not in the database anywhere. Yes?
But you still have to check every single spot.
I had it still at a what?
Check every single spot.
No, I didn't. If I hash to 2, but I'm not in the database, I go to spot 2, I see a status of 0, I didn't have to check every spot. I checked one spot. Yes?
So, but saying, so an example, if this was twice the size, right, and there are empty spots,
Yes.
and you aren't in the database, it would just go until it sees a 0.
It just keeps going, and at the moment it finds a 0,
Right.
then it knows it can give up. If it sees a -1, it has to keep looking. If it sees a 1, what does it have to do? All right, we'll look for Manal. I see a -1. Keep going. I see now a 1. What do I do? Check the key. Does that match Manal? No. Keep going. Does that match Manal? No. Keep going. 1. Does that match Manal? No. Keep going. 1. Does that match Manal? Yes. We have found Manal. I can go grab the data, and this is a typo. You had 0, but it looks like a 6, so you get $6 back. Does that make more sense? So we can deal with deletes, but it does give us a new bad condition. What if you're constantly adding and removing? Let's say I've got 8 values in here, I throw in 6 students, then I get rid of 6 students, then I throw in another 6, and then I get rid of those 6, then I throw in another 6, and I do this 100 times. What's going to happen to my statuses? Will there be any zeros left? No, what will my status consist of? Negative 1s and 1s. At that point, if I look up a piece of data that doesn't exist, what do I do if I only see negative 1s and 1s? I got to keep looking through the whole array again, correct? So you also have to rehash on many insertions and deletions. So you have to rehash if you need to resize because you need more room. But if you also use your hash table a lot, there's lots of removals, you have to rehash just to clear out all those 0, to clear out all the negative 1s. Overall though, the array-based hash tables get the job done. They're fast, and you can do a handful of tweaks on them. I've got a version of a hash table I use that's multi-threaded. I can have multiple threads all independently using the hash table at the same time. It's really weird, but it's really powerful and I like it. But I have a problem. I have to rehash it. So every now and then I just have to tell all threads, everybody stop, rehashing. Okay, now all threads, you can do your work again. And it turns out that that's an acceptable, rehashing is totally acceptable for me. Any questions on this so far? All right. How would the array of linked list based approach work? If I want 200,000 linked lists, what do I do instead?
Use arrays.
What?
Use arrays.
You don't like the idea of 200,000 linked lists? It's actually easier. No, 200,000 linked lists. I will start by creating an array. I will draw my array going down. This is an array of linked lists. So every array index is a linked list object. Does that make sense? So let's draw this. This guy equals linked list. Whereas this guy was array of linked lists. So now let's say that somebody hashes to a 3. What do? I would go to index 3, and what do I put in index 3? I put in a node. And what do I put inside of that node?
The key in their page.
And I would want to put inside of that the key. I'll actually make my node store a key. And what else do I store in there? The data, which could be some kind of an object. Does that make sense? The object of the stuff to store. And the key, of course, is our key that we're hashing on, say a W number. Now let's say somebody else also hashed to 3. What would I do? Would I say, uh-oh, someone's in 3, I better go to 4? No, what do I do?
Create another node and point
Passing on the list.
Yeah.
Just go down the list. Was that difficult? No, it wasn't. Let's say our first one was Esther, and of course, we get rid of Esther. Can you get rid of nodes out of lists easily? Yes. So is deletion now really a problem? No, it's not. Do we have clumping? We had a problem with Manal and Alexis. Was that same problem going to show up in this approach? Are they going to affect each other?
You can.
No, Manal wanted to go to 3, ended up in 7. Alexis wanted to go to 6, ended up in 1. In the new approach, Manal wanted to go to 3. Where does she go? 3. Alexis wanted to go to 6. Where does Alexis go? 6. Do they affect each other in any way? No. Therefore, there isn't that kind of a clumping problem.
There is a different one.
What?
Suppose everybody just goes to 3.
Why would everybody go to 3 if you have a SHA-256 algorithm that prevents that from happening? I guess if you're the adversary again, saying I'm going to specifically pick something that I know fills up that one particular bucket, but even then it's a little bit better. Like let's say, hey, I'm going to go pick a bunch of values that I know the SHA-256, when I mod it, will hash to 3. Okay, I fill up bucket 3. Have I run out of memory space yet, like I did before? No, what did I do at worst? Slow it down.
You're on the dice.
What was that? It has to go through all of memory space. So very quickly, let's talk about goods and bads of this. What is good and what's bad? Name something that's good or bad about this approach. I need more than that. No clumping with each other or with neighboring buckets. No clumping with neighbors. That's one. What else? Easy to delete. What else? Do we have to rehash if we hit capacity? Do you really hit capacity? No, so you don't have capacity problems. Yes. Why would you need to go outside of the 200,000? If you mod by 200,000, then you will always be within 200,000. Does that make sense?
Yeah. If you get more than 200,000 students, you're still...
Yeah, then now your bucket's starting to fill up a little bit. So you would only really rehash when the performance starts to really degrade. But you don't have to rehash because capacity, or you don't have to rehash because you had lots of insertions and removals.
And you don't have to, yeah.
Does that make sense so far?
So I have a question.
Yes.
Scale wise, so obviously in a small but not that much data, the speed difference is the same, right? Or you're not going to notice the speed difference, right? Like with only eight spots in the array, with only 8 buttons.
Well, yeah, but the whole point of this class is not doing stuff for 10 items or 100 items. It's scaling up for millions.
So at what point does the speed become noticeable?
That sounds like a good homework assignment. What do you think?
I'm still wrapping my head around scale, so I don't know. I honestly don't know.
Let's talk about it on Monday. That's a good question for Monday. No, so I bring this up because I love timing assignments. I think they're fun. Which one goes faster? And every assignment I've given in the past where students have to time to figure out what's faster, they come back and say, that was the worst assignment of the year. That was boring. Like, didn't you even care the results? Yeah, but it wasn't fun. But I want to do one. I would love to time. I'd love to implement both and time both. And verify and see if we can get a feel why it is. I think you need to have a good understanding of what makes these things fast and why are they fast and just how fast is fast, instead of just talking about it. So we only have 10 minutes to go. I just gave you a homework assignment, but there can be lab time. Let's get a number out the door. 673 652. That's a good number. This is a number you would use for a June 13th quiz. Online students, do you have any questions for me? Oh, I do need to talk about the homework assignment. Let's go over that. All right, so I've got you this file. This one's a bit different from past assignments. The reason it's different, yes, it compiles right out the gate, but the reason it compiles right out the gate is I commented everything out. In previous assignments, I would at least give you a lot of the scaffolding ready to go. And that way, hey, I've got your methods already declared, you just have to put the method bodies in here. In this one, I have not given you that level of scaffolding. So in this spot where I say to do, guess what you have to do? Supply the iterator class. And supply everything that needs to go inside of the iterator class. It needs to be templated. And the instructions tell you it's pretty straightforward. Hold on, I actually did create the iterator class for you. This is the iterator methods. Here's the iterator class. The reason I gave it to you is in order to make some of my stuff work right, I needed to inherit off this STL tools trick. I also friended for you, but you have to do all those iterator operator overloads. You also have to supply the 2 data members for the iterator. You also have to go to your linked list class and supply the begin and end method. These create the iterators. So you're inside the doubly linked list class. The whole point is this creates the iterator in the class. Remember my nature looking examples where I had this green iterator being birthed and pulling outside of the list object? That's what these are. So you have to make a begin and end method, and then you have to implement the begin and end method. I think I told you to do it right here. Here's a great place for your begin and end to go. Make sense so far? If you get those working, you can start uncommenting these tests. So you can start commenting and commenting out test iterator fundamentals. Note that you don't have to do all of them all at once. You could comment in just say the first one, the first 2, just to verify, can I at least make an iterator with begin, and can I plus it with the prefix? So if you don't want to do everything, you can just do 2 things and test it. Is my begin method working? Actually, there's 3 things. Here, now it's 2. Is my begin working, and can I dereference it to get to my data? If you get that working, great. Comment in the next test. Can I plus it? Great. If that works, can I check my not equals? And so on. So you can keep turning on tests, testing them, and limiting yourself to certain points. Make sense? And then there's more with test iterator increment, where I say, let's see what happens if you just do a whole bunch of pluses in various scenarios. How about decrement? Can you make your iterator go backwards in various scenarios? How about test iteration tricky? What happens if you have a 1 node list or a 0 node list? Does it blow up your code? Then I do something called algorithms. And algorithms are interesting. I load up some data in this order: 2, 4, 6, 100, 8, 10, 12, 100, 14, 16, 18, 20. And then I want you to sort that. But in order to sort it, what do I give you? 2 iterators. This is a weird new way of thinking, a very powerful way of thinking. Here is your sort function. What's begin? What's end? They are iterators. Using only iterators can you sort. How would you sort? Can I ask, let's draw a picture of it. Two, 4, 6, 100, 8, 10, 12, 100, 14, 16, 18. Where's begin at? Begin is at here. Where's end at? In this quasi section, kind of like right here, correct? Could I make a copy of begin? Sure can. You can easily make copies of iterators. I can make a copy of begin and have it point here. Could I make another copy of begin and increment that guy forward? Yes, I can make a copy. Just here's a new one. Could I then plus it? Yes, so I could have 2 iterators, one pointing at the 2 and one pointing at the 4. Could I then say, is this iterator less than that iterator? Yes, but I would have to dereference him first. I dereference this guy, is it less than that guy? If it's less than, then I don't have to do any work to help sort it. What if it's bigger? I might flip it around. I've given you the entire algorithm for your sort in English right here. You can do every piece of logic with only iterators. So again, when you're working within our sort, do you have access to nodes? No, you have access to iterators. Can you ask the node for its forward or for its backward? No, you have iterators. Can you ask the list for its capacity or its count? No, you have iterators. Can you still get it all done with just iterators? Yes. If you get it all done with iterators, guess what that means? You have written a sorting algorithm that works not just with your linked list, it'll work with any container that supports going forward and going backwards. Is that powerful? That's crazy. You just wrote a sorting algorithm for somebody else's data structure. And it works, as long as they support iterators. So we can talk about this more on Monday, but just know that's what you need to do. I gave you in English what you do. Just turn my English into iterator code. All right? All right, I'll get you a new quiz on Monday. We'll talk about arrays and speed more on Monday, and let's go from there.